Let us get started. So, welcome to Chem 201, this first semester or sort of first half of the sequence of general chemistry. Sort of the full what we expect people to know of chemistry really is covered in 2 full semesters, this being a somewhat intensive first half, trying to cram a lot into a relatively short amount of time, and admittedly a short amount of time these summer sessions. So, we'll dive in, we'll get to it. As sort of a general rule, I record these lectures so that you have a copy of it in case your note taking is not as fast as my speaking, as well as it's a good thing to reference time and time again. So these will be posted on Moodle after this lecture. You are still encouraged, if not strongly suggested, to come to lecture as you'll get everything in person. But if you need to miss things, these are of course recorded. So we'll do introductions. I'll introduce myself first, and later on, I won't make anybody do public speaking, but we'll get to know each other a little more. My name is Kelsey Sakimoto. I'm your professor for this course. I like to know where people come from, so I tell people where I come from. I was born and raised in Honolulu, Hawaii, so I'm very, very far from home, and I've been far from home for a number of years, being here in Boston for coming up upon a decade. But I very much consider most of my formative years spent in my little tiny island home. I'm very interested to learn where you all come from. My background, why I'm qualified to teach you, and a little bit about where my perspective is coming from. As an undergrad at Yale University, I was a BS in chemical engineering, so I have a bit of engineering background. Some of you I know will be in my engineering class this summer as well. From there, I moved over I went to the University of California at Berkeley to do a PhD in chemistry, spending a good amount of time sort of diving deep into the forefronts of knowledge of chemistry. But they have slowly sort of been wandering, drifting since then. When I came back here to Boston, I spent a good number of years doing research in microbiology, sort of very much adjacent to chemistry. From that microbiology experience, we spun out a company, a startup, which is still sort of going out in Natick, in sort of the biotech world. And then since then, I have been very much coming back to the world of teaching here in chemistry and, of course, engineering. I also teach at Wellesley. I teach organic chemistry there as well. And my research sort of generally falls into the realm of recycling and upcycling waste materials into all the fundamental chemical building blocks that we use for our daily modern lives. Things I enjoy. If you ever want to talk to me about fun things that aren't chemistry, I'm a big fan of Broadway musicals. I've been told, and I think I do give off theater kid energy every once in a while, but I'm also very poor, so I don't go to them. I watch bootleg recordings of them on YouTube. I'm a big nerd, and I particularly love puzzles and things that have elements to be solved, so I'm a big fan of tabletop games like Dungeons and Dragons. And I do go outside. I am on a sort of maybe lifelong mission to collect all the embroidered patches from the national parks here in the US and abroad. Here is a photo of myself with my wife at the Black Canyon at the Gunnison, with a lovely pegmatite and nice rock formation in the background. And as I sort of suggested, and the reason why we are starting a little later than normal is I do have a very young daughter. She's about 9 months or so, so still very much a wee little thing. She is a very serious baby and communicates when she's unhappy, such as this morning. So the reason why I show you this is, of course, to show off my very cute baby, but to sort of place the understanding that everyone's lives is very busy and complicated, including my own. And so I have a strong dose of understanding if things don't work out, if you are running late to class, if you need to miss a thing. Very much in the same boat. I come from a very sympathetic standpoint in that. So that's me. We will sort of get to know each other in the intervening weeks here on out. A little bit about myself. So I think every teacher that you have should lay out something of a teaching philosophy, which lays out what my expectations are, what my job is, why I'm here, what I'm giving to you, and sort of where you fit in this equation with the rest of the world. My teaching philosophy I summarize as this. There's sort of three groups in this equation. The rest of the world, myself as your teacher, acting as an intermediate between you as students and the rest of the world. By enrolling and coming to this college, and of course coming to this class, you're telling me and Bunker Hill what it is you want to do, whether it's becoming a scientist, an engineer, a doctor, whatever it might be. You're telling me you want to do something. And my job as your teacher is to glean the infinite knowledge of the world and try to figure out what is it the world needs you to do, needs you to know how to do, and expects of you. From that infinite of things, that list of things that you could know and could learn, I'm trying to reduce it down to the essential things you have to know to enable you to move forward in your careers and to achieve whatever fulfillment you would like. In that process, I try to filter, give context to, and simplify sort of very, very complex ideas. One reason why taking a course from Bunker Hill is very different than just reading Wikipedia articles. Filtering information is very important to learning. Over the next 8 weeks or so, we go back and forth. This is an iterative process in which I tell you what you need to know, and you demonstrate what you have learned so far. And we bounce back and forth, tailoring the material all the way into the very end of the semester, in which I report back once with your final grade to tell the rest of the world how well you know chemistry, or at least this aspect of chemistry. There's a few consequences to this philosophy. One is that this is a dynamic process, it's iterative. This process of going back and forth means that this course does change as we go along, as I get a different assessment of how this cohort of students is learning material. Some things might change, some problem sets, lectures, other things might be tailored. So things are dynamic, things will change. Be prepared for that, but it is to your benefit. The other big consequence is that I only report back to the world how you do, how well you know this aspect of chemistry once at the very, very end of the semester. I really don't care how long it takes you to learn things. You could do zero work until the very, very last day of class. Not advised, not recommended, but it doesn't, I do not require you to learn at a certain rate or to pick up material at a certain pace. Uh, that does mean that it is on you to be very truthful with yourself of how you need to keep your self-discipline, how you need to keep things up. But I'm not going to dictate how you learn or how quickly you learn material. I only care that by the very end of the class, you've learned a core set of chemical principles. There's a few elements of this teaching philosophy. One thing that we will adapt to each other's teaching and learning styles. If you haven't ever really thought about it, or no one's ever told you, we as teachers, your professors, instructors, recognize that there are many different ways in which you all as students learn. From a very scientific standpoint, many people are visual learners, in which the best way for you to gain information is through visuals, through diagrams, pictures, other things you can see. Many other people are oral learners, so you need to hear something said. You need to listen to a podcast. You need to listen to lecture. You need to hear it to process it through that portion of your brain. Many people, or hopefully many people, are reading and writing learners, in which you need to read something. You need to read a textbook, take notes by hand. That process is the best way for you to commit things to your deeper knowledge centers. And then many people, myself included, are kinesthetic learners. I mean, you need to touch and hold and feel something with your hands. In chemistry, we use a lot of molecular models, things that sort of represent tiny, otherwise invisible molecules, and we try to turn the invisible and intangible into something you can hold and touch and manipulate as a kinesthetic learner. Now, most people are going to be some combination of all four types. But it's very helpful for you to be aware of what type of learner you are, what is most useful for you. If you require, or if you're an oral listener, oral learner, that means you probably do need to come to lecture and you do need to listen to the things that I say. If you are a reading and writing learner, it means you probably do need to read the textbook either before or after the lecture. So as we go through this, if you haven't already, be aware of what type of learner you are, explore that, and see what way works for you best. Inherent to all that we do in chemistry is that, potentially different than some biology classes you may have taken, chemistry is very math and equation focused. It's a very quantitative science. And so there's no getting around that. There's no dodging the algebraic and numerical skills required, but we of course build towards that, and there's ample help to get there. We can't dodge the equation, the math around chemistry. A lot of what we do is also word problem based. It's not applied chemistry. I don't ask questions just for the fun of it, just because they're interesting things of chemistry. I ask questions because they relate to real-world problem solving that you'll encounter both now in your normal daily lives, but as you progress through the rest of your future. A lot of that requires good reading comprehension to be able to extract the equations that you solve from these word problems we set up. Again, we sort of build towards this. There's ample help, but make sure that you are honest with yourself on your ability to work on these types of word problems. Finally, the last thing I'm here is that even if only a few of you will become chemists, it's important to learn how chemists do things, how we think about things, what this chemistry perspective is. Many of you will work with chemists. Many of you will benefit from understanding a different way to solve problems and approach things as chemists would approach and solve them. Some of it means that there's many ways to do things. Some of these concepts might be reviewed from previous classes you've had, but take it as an alternative perspective, a different viewpoint on the same material, as a way to understand a different way that different scientists tend to think about things. So obviously, I have a teaching style and you have a learning style. We will adapt to each other. Of course, figure out what type of learner you are. The more that I know what type of material to prepare, the better I can anticipate and provide you what you need. By and large, I try to present all of our material in at least two different ways. Everything we talk about, 80–90% appears in our textbook as something you can read. 80–90% appears in our lectures as something that we can talk about, we can hear and listen. And some overlap with that, of course, exists in our lab experiments that you can see, visualize, and touch and feel. The more I know about how you learn, the more I can prepare tailored material towards your learning type. A lot of what we do in chemistry, of course, builds upon what I call the soft skills of being a student and being a student in science. Important things to be honest with yourself about is, do you know how to take notes during lecture? Do you know how to be a good student? If not, we can help you get there. But make sure you understand what you need for success. This class, of course, has homework, as every science class does. Do you know how you best complete homework? Do you need to work on it by yourself? Do you need a study group? Do you need one-on-one time with your instructor? Each of these things requires a little bit of self-reflection, and this is the perfect time to do a little bit of self-reflection to figure out what it is that you need to be successful. I am here and I am more than willing to provide you whatever it is you need to be successful, but everybody will require something different. I can try to make my best guess, but the worst thing you can do if you find yourself not comprehending something, falling behind the material, is to just come to me and say, I don't know anything. I don't understand anything. It doesn't help me help you if you don't know what it is that you need. The more you understand about yourself, the better I can provide what it is that you need. So do take this seriously. Do take a moment to think about what do you need to be successful in any course that you might take. A big part of my teaching philosophy, again, getting a lot of this business out at the beginning, comes around the idea of new tools, which many professors have different perspectives on. I have the perspective, being a scientist for many years, is that scientists use whatever tools we can in order to be faster and more accurate than what we were yesterday. Historically, we have always gravitated toward using the most newest and best tool we can. If you were a scientist before the 1960s, you probably had in your pocket a slide rule, an ancient piece of technology that allowed you to manually calculate complicated math like logarithms and exponents. Many professors in the 60s were very proud that they knew how to use a slide rule and prevented people from using things like calculators when they came out because there was a sense of honor and history around that. If you're a scientist up to the 80s or so, of course, calculators became more widespread, and scientists were the first to adopt this new tool that did a lot of the math for us, prevented us from having to do mental math or complicated sums on paper. And of course, nowadays, everybody, or nearly everybody, has one of the most advanced computers in the history of mankind in their pocket, which of course does indeed also have a calculator. I want you to use every tool that is available to you, that is at your disposal, because once you leave this class, there's nothing that's stopping you from using your phone to calculate things, to look things up on the internet. And so as a scientist, we use any tool. I want you to use any tool to be faster and more accurate being the key statements. Now, this comes with a caveat. In general, I have an open resource policy, which means that any homework, problem sets, exams, whatever graded material for this course, you're welcome to use anything that you like. You may have your phone, you may have the textbook, you may have our lecture slides, you may look things up on the internet, Google, Wikipedia, whatever it is. You may use all these fancy new ChatGPT natural language models or large language models. During all these things, the only thing that I don't allow you is any sort of messaging or texting apps in which you directly talk to or communicate to someone, a friend who may know chemistry better than you or who may be able to provide that type of assessment. I give this with a caveat that all these things are fantastic to be faster and more accurate. I myself have rarely memorized anything if I know that I can just look it up on Wikipedia. Of course, I don't allow you to get help from another person, since that tests how much they know, not how much you know or how much you're able to do. And I give this all with the caveat that particularly the newest tools like Google, Wikipedia, and AI models are very, very fast. You can type a question in there, you can type my homework questions into there, and it'll spit an answer back at you in fractions of a second. But they are not very accurate. In the last year or so, we as faculty have all explored these natural language models and figured out what they do and what they're able to do. And the way you should treat them is that they are a very smart friend who's always at your disposal. But like your very smart friend, it doesn't mean that they're infallible. They make mistakes. They can get things wrong if they look up the wrong bit of information on the internet. And you shouldn't trust what they say blindly, because they make mistakes. And ultimately, they don't care if you pass this course or not. ChatGPT doesn't get any more money if you pass this course or you fail. So do treat these with a element of caution, a grain of salt. But otherwise, use the tools that you need, make use of them, know how to use them correctly and how to use them very accurately. And we'll work on that throughout this course as well. Throughout this course, there are a few objectives. Ultimately, because not all of you are going to become chemists, and my job is not to convince you to become chemists, my main goal is the idea of chemical literacy, to know and understand chemistry in a way that gives you a basic intuition for how the atoms and molecules of the world around us work, so that we can begin to glean interesting new science, things that are new in medicine and materials and food and energy, and be able to separate that out from things that are obviously misinformation or slick marketing or misunderstanding what is plausible, reasonable chemistry versus impossible, improbable chemistry. That's a big element of chemical literacy. The other big part of it is to know how to use appropriate tools. In this course, we make abundant use of our periodic table of elements. And it is a tool, very much a map that we'll talk about next week. But beyond knowing it exists and knowing how to find one, it's important to know how to use it, how to navigate that as a tool, as you would a map. Finally, the last thing is a bit of problem solving. As I said, chemists approach problem solving the same types of problems in medicine and health and energy and materials that many other scientists and engineers do, but we approached it in a particular chemical way that I would like you to have an appreciation for and employ as you see fit. To get there, again, this being the first half of this Gen Chem sequence, we cover a few topics. Today, we work on our chemistry fundamentals, our baseline of how do we think of science in the frame of chemistry, how do we think of the material world, and how do we think of the analytical side of it, of making measurements, recording data, reporting that data. From there, next week, we begin to dive to the smallest level of matter that we talk about, to the individual atom, ultimately trying to understand how this map of the elements allows us to predict the properties of that element based solely on its position, what row or column this element will be found in. From there, we begin to build up from atoms. We begin to assemble those atoms into molecules, trying to understand the relationship between a molecule's or a chemical's name, the structure of that molecule, ultimately how we use that structure to predict the properties of that molecule, how it behaves, how reactive it is, what it reacts with. Is it toxic? Is it dangerous? Does it explode? All of which we can get simply from the name and structure of that molecule. In the back half of this course, we again, of course, dive into chemical reactions, trying to be able to predict plausible ways in which chemicals might react. You'll need to wait until the second half of this course in 202 to be able to predict what actually happens, but we begin to sort of figure out what is plausible and possible in chemical reactions. Some of it is simply trying to relate things we experience in our normal everyday lives to more rigorous chemical principles, such as the idea that you hopefully have heard that you should not mix bleach and ammonia at the risk of forming very toxic fumes that do kill people more often than it should. We begin then to sort of move from the world talking about individual atoms, molecules, sort of this abstract world of chemicals, to now talking about them in their bulk phase. Rather than individual molecules or atoms behaving, how do they behave as a bulk material? Trillions upon trillions of atoms together as a gas. How do we predict those properties as we'd experience them in the real world? And then finally, the last thing we'll talk on is the idea of thermochemistry. Ultimately, the two halves of the physical world are mass and energy. We spend a lot of the first portion talking about mass and matter. The last section we begin is sort of an intro and primer to how we talk about energy and how energy ultimately dictates not just what is possible, but what is probable, what chemical reactions actually do happen, and how to predict that. Logistically, there's some course business. This is a very, very quick course, condensed down to the summer semester. So make sure that you have all of the logistics worked out as best as possible. Hopefully you all have been able to access or will soon access Moodle, which is our online portal for this course. It contains nearly everything that we do in this course. It has all of our reading assignments for our textbook, problem sets, which you will do and turn in for a grade, as well as that is where I keep my grade book, so you can keep track of how you're doing throughout this course. So make sure you're able to navigate and figure out where all these things are on Moodle. There are a few things that are required, and some things that are suggested for this course. Because I have no love of textbook publishers and they don't pay me anything special. We are using an open resource version of a chemistry textbook. This one, Chemistry Atoms First, comes from OpenStax, which is a project out of Rice University that tries to make these textbooks here in general chemistry, but other subjects as well, free, available as either a PDF or a website through the links available on Moodle. You can also order a physical copy if you're a physical book type person. I am myself, and these are relatively cheap. You order them directly from Amazon for about $60 or so much more affordable than the several hundred that most textbooks require for you. So make sure you have a textbook. There are things in there that are helpful to complement what we learn in lecture. You also need to be prepared for lab, and that mainly comes in the form of safety goggles. There are many different options out there. The announcement on Moodle that's currently pinned gives you some options, some Amazon links where you may buy your own. But I do suggest that whatever ones you buy, to make sure that they are comfortable. The thing that I know well beyond anything else is that if safety goggles are not comfortable, they do not fit your face appropriately, you will not wear them and they will not protect your eyes. The main thing that you need to figure out for this goggle is that you may use any goggle that carries this ANSI ANSI, which is a US standardization organization that carries this Z87 rating. This rating, you may see as Z87, Z87.1, Z87 plus, all sort of meaning the same thing, means that they are approved for the type of work that we do. Mainly, they include two features. One, they're made out of shatterproof plastic, so that if something hits this, it won't break into a million pieces and go into your eyeballs. It also features a side splash guard, so it protects your eyes from the side in case your neighbor to the right or left of you fucks up and creates something that would splash into your station. So you're welcome to pick any pair that you like. There are many different options out there, so you're welcome to sort of shop around. But all of them sort of feature the same sort of designs, but fit your face quite differently. For myself, and I'm told people with Asian noses, my safety goggles feature nose pads, which are adjustable, that make sure that when they sit on my face, that the bottom of these goggles don't touch my face, which would be very annoying and would make me not wear them. I have these because these don't fit my face quite as well and touch here and are very annoying. And so I've learned through the years to buy the ones that fit my face. You're welcome to try things out. They're relatively cheap, so you can always buy a couple and uh, I'll buy them from you if you ultimately don't want them. You can sell them back to me. But you'll need these safety goggles for lab on Wednesday. You're also recommended, but not required, but recommended to have your laptop or a computer tablet or a very large screen phone for lab in an effort to sort of reduce the amount of paper that we produce for this course. We have moved towards digital versions of the instructions for each of these labs, for which it's helpful for you to have a device upon which you can view it. We have some computers in the lab, but they are not quite as easy to use, so I would recommend that you bring your own device. I will have printouts of anything else that needs to be printed, but you're encouraged to bring your computer. Logistics. So today being an unusual day, probably hopefully will not be this normal way, but we'll have lectures here on Mondays. We will go all the way through 2 p.m. on some days, but some days we will end earlier. We will break roughly halfway through, so please feel free to bring snacks, a lunch, whatever you need to get through a relatively long lecture day. These Monday lectures will be about going through sort of the material, trying to present it maybe for the first time. I will post the slides that we're currently going through on Moodle so that you can take notes on it if that's your preference. I am recording this as well so that if you need to listen back to it, it's available for you as well. During this time, you are encouraged to either actively listen. You're welcome to sit there and absorb it if that's the way you learn best. In many cases, you're encouraged to take notes, ask questions, get the most out of this time as you can. And to complement that, everything we talk about, or nearly 80 or 90%, is also presented in our textbook as a different way to phrase the same things. You're welcome to read it before or after the relevant lecture, whether you would like to read things first or listen to things first. Our other day, on Wednesday, beginning this coming Wednesday, we'll have our lab. We'll be meeting in 314, which is, if you take a left out of here, through the stairwell, continuing on what looks like professors' offices. Indeed, there is an entrance to the laboratory space there. You're welcome to follow me after this lecture if you would like some personal tour guidance. But during this lab period, we'll be doing experiments to help verify the things that we learn, as well as discover some new principles in chemistry. Unlike our lecture, the lab is an active space of things you don't want to ingest, so we will not be eating in lab, but you're welcome to bring snacks that you can step onto the hallway to drink and consume. It is, again, a relatively long day. The first 3 hours, from 9 till about noon, we'll do the lab experiments. Those are required of you. Those lab experiments all culminate in a lab report, which for this course is essentially a worksheet where you record the results of your experiment and do some analysis of the results that you see. The instructions are posted on Moodle, but I will be bringing printed copies of this worksheet for you to fill out and turn in the following week. These lab reports are due 1 week from the date that we do those experiments. From noon to 2 p.m. is an optional tutorial session. This class does have homework. We call them problem sets because they are sets of problems. And the latter portion of our Wednesday session will be an optional tutorial session in which I will go through roughly half of the problems, helping you figure out how to set up, how to solve some of the trickier bits of these problems to get you on the right foot and to give you some good momentum. You're strongly encouraged to come to those sessions, to stay in that laboratory space to get some guided tutorial through the problem sets, but you are not required to, of course. We can also work on any other material that you require help on. Some of the lab reports as well may be trickier. But it's an optional but very strongly suggested portion to get more tailored help in solving these types of questions. Questions up until now before we dive even further into logistical chat? If not, maybe the most important thing, at least as far as you're concerned, how will you be assessed and how will you be graded? So in this course, I will grade you according to Bunker Hill's normal standard grade, letter grade curve on 4 different categories. The first one being problem sets, these homework assignments that are to be completed and turned in 1 week from the date they are assigned. You'll notice that these problem sets are worth a very small portion of your grade, only about 10%. These problem sets are intended for you to practice and test yourself. These are not there to punish you if you haven't learned something yet or you're still struggling with a concept, but they're there for you to assess how well am I understanding the material, worth only a small portion, just to help keep us honest and on track. The next big chunk comes from these lab reports, doing science and having the skills to actually carry out these experiments and then analyzing the data that we see. About 20% of your grade comes from that. The biggest portion of your grade, 40% or so, comes from what I call proficiency badges. I'll say a bit more on this in a moment, but this is the way in which I assess how well you understand these core chemical principles. You may think of these as sort of Scouts merit badges that certify you in particular chemical skills, for which there are 20 things, 20 skills or proficiencies I need you to know by the end of this course before you move on to the next half of this sequence. This is the biggest portion of your grade, the thing that matters most of how well you understand these core chemical principles, worth 40%, and we'll say a lot more in one or two slides. The final bit, of course, there will be a final exam. This is a very, very standard final exam that will be on the last day of class, so the 29th of July, also a Monday. It'll start a little later, and we'll talk more about that as that comes up, but do mark that as a time that you need to be in town if you have plans to leave town much in advance of that. By and large, as I mentioned up front, I really don't care or how quickly you learn things and how together your life is not my overriding priority. People have busy lives and complicated lives, and I'm very sympathetic to that. And so I don't grade you on attendance. It is up to you whether you want to come. You pay to be here. It's all up to you. But of course, you are strongly suggested to come, and this course does move quickly. 1 or 2 chapters a week is quite a quick pace. If you have to miss something, lectures, of course, are posted online, but there is no time to make up labs. So if you have to miss a lab, you unfortunately will sort of miss out on that opportunity. You're welcome to coordinate with a friend to get some of the data so you can still do the calculations and do the worksheet, but I'll leave that to you to figure out. Even though I don't want to destroy your lives if you can't quite get things together on time, it's still important that as you move on in your professional career that you appreciate the timely delivery of work and a completion of assignments. And so every assignment is due by midnight on the day that's listed on Moodle. Most are going to be turned in here in class. Anything that is turned in after that gets deducted a flat 10%, and that's it. Whether you turn it in the day after it's due or at the very, very end of the course, they'll all get deducted the same little bit of your grade just to help keep us honest and help give us incentive to keep on track. Other than that, any assignment can be turned all the way up until the very end of the course, the very last day of class. It is my intention that you do the work and you learn things, hopefully on time. Now, these proficiency badges are really the main thing that I'm going to be testing you on. We don't have midterms as you would normally have them in this course. Mostly the way that midterms work is that I give you a test, you know some fraction of it. Anything that you didn't learn by the time the midterm comes around, you usually just say, I'm never going to learn that, and you forget it and you move on, which is obviously not very helpful to being a scientist. These proficiency badges are a way for you to incrementally and cumulatively work up to passing all the core skills that I need you to know. I have a list of 20 things I need you to know before you go on to Chem 202, the second portion of this sequence. And I don't care how quickly you learn those core skills. I don't want to punish you if it takes a little longer for the more difficult ones to sink in. As such, we run the system of proficiency badges. There are 20 badges, 20 skills, very much like a merit badge in Scouts, in which I need you to know and be able to pass a short written test by the end of this course. There are basically 2 sort of sit-down testing sessions in which you can try to test them and try to pass as many of them as you can. Like really any other test in the real world, whether it's a driver's test or the bar exam, you're welcome to retake the test and to continue to work, and you're not punished if you don't pass the very, very first time. Same thing for this. You'll work throughout the course over these two, maybe three testing sessions to pass as many of these short written tests, demonstrate that you know how to do a particular skill by the end of this course. The exact format, the exact sort of format of and rules of that we'll talk about when we get to one of those badge tests. But the list of things I need you to know are very much key concepts in chemistry that we will be picking up as we go along. There are things that relate to sort of the general business of science, using math to solve problems, working with units in chemistry, understanding how atoms, bonding atoms and molecules work, as well as chemical reactions, gases, and thermochemistry, all key essential skills that we need you to know before you move on. Each of these essentially represents one badge, one sort of short written test to pass and get certified in that you'll continue and work throughout the course to get as many as you can. Likely this is new, likely this is something that you have not encountered before, and so there are undoubtedly many questions. If you have a really pertinent one, happy to talk about it now, but more will become apparent as we move through the semester. There aren't any big pressing questions before we clarify later. A brief overview of what we'll be doing. A short course, but very, very much jam-packed. Each week we'll have lecture or a badge test and a accompanying lab that helps reinforce the ideas that we've learned. Our final exam here on the 29th, the last day of class, and then the badge test and a brief review session as indicated. This schedule is pretty locked into place, so make sure that you don't have any travel plans on any key dates, or if you do, please let me know now so we can try to work out some sort of arrangement. My last little bit of logistical things before we do a little activity and then a lot of chemistry is my tips. I say this now because it bears repeating several times throughout this course. There are a few things I've learned from teaching this and several other courses on how students can be successful in this course in particular. You should come to lecture. You should take notes. Even if you don't think you're a reading or writing learner, I can almost guarantee some part of you is. It's helpful for you to actively be engaged in this material and not just listen to a YouTube video in the background as you do other things. Do the homework. Doing the homework is important, one, because some things are best taught and learned by doing problems, by carrying out calculations or solving things on your own. So they're an important part of how you learn material, but also how you test yourself, of how well you understand what it is that we're teaching. Do those problem sets, but don't treat them as something that is the only factor of your grade. It is better to turn something in that's only 60% correct and get the feedback and get an idea of what the correct answer is than to hold all of it until the very end, hoping that you can get a perfect score, which very rarely, I would say, never happens. So do them, but don't treat them as the most important thing that you are assessed on, but a tool for you to help you learn. Some people take me up on this advice, but you should be making yourself a cheat sheet or a study guide, a single page, 2 pages or so that summarizes all the key information, key concepts, equations required for this course. The allure of our open resource policy makes you believe that when the exam comes, I can just look things up on the internet, and I can guarantee you that I've seen many, many students fall into this pit hole of thinking that I can just Google an answer and then spend half of the test period trying to figure out one answer to one question. There's a lot of information out there on the internet, not all of it helpful, useful, or accurate. The more you can navigate that information and have something for yourself that you trust and you've vetted and verified, the faster you'll be, and speed is quite important in this course. Ask for help. Whether it's sort of being shy or an element of pride, everybody will need help in this course. Everybody will need to talk to me at least once and ask for a clarifying question or some help on a particular problem. Very few people are able to go it on their own, and that's expected. That's the reason why you take this course and are not just reading a textbook on your own. The best students I've ever had are the ones that ask the most questions, the ones that try to check their understanding as much as they can. If they don't understand it, they ask for help, and they ask for me to help re-explain it or say it in a different way. I can't magically predict who needs help and who's struggling and who is not getting things. I can only do so if you tell me. There are many people you can go to for help. I'm obviously, of course, a very good resource. I know a lot of chemistry. You're welcome to email me. You're also welcome to text me. That is, of course, also on Moodle. Don't call me. I don't answer phone calls because there's a lot of trash calls these days. But you're welcome to text me. If you text me, do say who you are. Don't just send me random texts because I have no idea what your numbers are. So do introduce yourself, but do ask for help through any means that you find helpful. Your classmates are your best resource in many instances. They understand sort of where you're coming from in terms of learning this material. So do make friends, or classmates at least. You don't have to be friends. But find at least one person in this class you can go to work on problem sets together, to clarify something you don't understand, to ask a question. Finally, Bunker Hill does provide you a lot of resources to be successful. In particular, if you do require some alternative testing or other arrangements, please do make sure that you line it up with the DSS early and as soon as possible. They are notoriously slow for how crucial their job is. But in many cases, if you require extra time or a low distraction testing environment for whatever reason, do let me know up front because we can begin implementing that ASAP. But the official letter from DSS does take a moment, so make sure you work on that soon. Finally, the last thing that I always encourage you is that it's hard to be a chemist, it's hard to be a scientist. You may be super smart, but it's hard to do so if you're not secure in body and person. Bunker Hill is very mindful that living in this world is very expensive, and so things like the Dish Food Pantry, which has a lot of free resources, both food and consumables, but also things like personal hygiene and other things. If you have babies, they have diapers and infant formula, which is very expensive on its own. All those resources to make sure that the distractions of being a person outside the classroom don't interfere with being a student here in the classroom. So make sure you take advantage of those resources. Questions, logistical things before we dive into a little bit of chemistry towards the back half of our time together. As usual, please do sort of send me emails as questions come up. Even if you just want to say hi, please introduce yourself. We'll get to know each other a little bit, but don't be a stranger. Don't sleep on the great resource that I am. If there aren't any big pressing questions, let's dive into a little bit of chemistry. So chemists really come from a very, very ancient and very, very odd history of alchemy, which is this sort of very ancient, now very strongly debunked branch of pseudoscience that tried to manipulate parts of our material world. Many early alchemists, such as Henning Brand, here depicted in this wonderful portrait by Joseph Wright. Henning Brand was an early alchemist that, like many alchemists, tried to do what we now understand to be impossible things. Alchemists tried to turn things like lead into gold simply by burning in the ground and waiting a bit. Henning Brand accidentally did some really important chemistry. Henning Brand was trying to find the Philosopher's Stone, which, as depicted in Harry Potter, was a mysterious element that did really everything, but importantly granted eternal immortality and everlasting life. And Henning Brand, it's hard to say why, but thought that he could make a Philosopher's Stone by taking several gallons of his own urine and boiling that down and removing all the water. And he did so, and he created this really disgusting vat of hot boiling urine and boiled it down till all the liquid was removed. And at the end of that, he produced this glowing white rock, which he thought must be the Philosopher's Stone, because what else could it be? Unfortunately for him, it was not the Philosopher's Stone, but rather it was his discovery of the element of phosphorus, which, like the material on the tip of a match, is a material that burns an intense white color. Much of what he did as an accidental chemist was very important, of course, and we build off of that legacy. But ever since then, chemists have been trying to be a little more purposeful, a little more precise, and more effective in our discoveries of how the world works and how you might make new inscrutable things. Importantly, they sort of discovered this idea that there was a difference between physical and chemical changes. Physical being ones that just change the form of that matter, taking liquid water and boiling that into gaseous vapor, and distinctly different than chemical changes, one that changed the composition or the sort of structure of the materials around us. Unfortunately, what they had a problem doing was trying to predict not just what they thought might happen. They thought that you could boil urine and produce a stone that gave you immortal life. But being able to predict what actually would happen would require a little bit of chemistry. And really, what chemists have been able to add upon alchemy are three things. One, we spend a lot of time, and we'll spend a decent amount of time in this course, trying to figure out what things are made of, trying to figure out what is in urine. We won't specifically look at urine, but trying to figure out what is in these different substances around us and trying to figure out, could you find phosphorus in urine? Could you find gold in urine? Which of these things are reasonable based off the composition of the matter around us? From that, chemists worked very, very diligently to come up with rules, mainly rules that gave us a predictive power, things that allow us to predict if I boiled urine down to dryness that it wouldn't produce a stone of immortality, but a hot glowing rock of fire. Most of our time in this course will be spent trying to learn what rules have been so far predicted and trying to figure out how we might come up with new rules to help predict how things behave. And the final thing that chemists really added to the equation was standardizing how we talk about science. Most of us have a natural instinct for science, to experiment, to investigate, to learn how the world works. But the beauty of chemistry and of science in general, as a formal practice, has been our ability to standardize how we talk about stuff so we can communicate to other scientists what we did, what we saw, and what they might expect to see if they ran the same experiment. Only by the standardization do we allow ourselves as scientists to work together, to be able to collaborate, to build upon each other's knowledge, to not each individually reinvent the wheel over and over again. This may be the most annoying part of science, trying to follow the rules of formatting and convention and how we name things, but it's important to not just being a guy boiling urine in your garage, but being a very professional scientist who may go on to win a Nobel Prize. The first thing that we spend most of our time, and we'll begin here today, is we want to figure out what things are made of. We look at the world around us and we probably have some instinct about how certain things behave, things that we've encountered before we have firsthand experience. I am very happy to touch this paper because I know that every time I've touched paper before, it hasn't exploded in my hands. It's not poisonous, so it won't hurt me. And other sort of properties I've experienced firsthand. But a lot of what we encounter as chemists are things that we've never touched before, that we don't know if it's safe to touch. How do we go about predicting what is this material, what is this substance, and what are the properties and how I should treat it or how I should observe it behave? The first sort of big category that we begin to divide the world is how many different things being a very loaded word, how many different things make up these substances we see around us. We'll look at three different substances to begin with. Diamond, which maybe some of you have, dry ice, as well as crude oil, sort of the thing that gets refined into gasoline. Now, in a very lazy description, all of these are some form of carbon, but they're obviously not the same material and behave very differently. Diamonds are very stable and very valuable for that reason. Dry ice is very cold and turns directly from a solid pellet to a gas. And crude oil, of course, burns and creates a lot of energy. In classifying matter, we really want to be able to say not just all those things have carbon in them or they're made of some sort of carbon, but try to be a little more precise in describing what are they made out of and at what level are we beginning to categorize or inventory what makes up those elements. A lot of what we do on the categorization and classification really matters on the length scale that we're talking about. Chemists often consider themselves as the central scientists, ones that sit between biology and physics, largely because we look at this range of length scales that varies from the experiential level, what we can see with our naked eye, down to the invisible, down to this atomic level. Again, a lot of it matters on what length scale we're looking at. And the first way that we might categorize a material is it homogeneous, uniform in composition? When I say homogeneous, what I mean by that is that if I take a certain amount of that material and I sample it, I point to a position in that material, I point to another spot, I point to another spot. Is the composition, are the things that make up that material the same regardless of what point I point at? Let's take an example, a big analogy, and this is an aerial shot of Bunker Hill's campus. And I can say that at this length scale, if I was to point anywhere here within the athletic fields of Bunker Hill, anywhere I point to, I could probably say it's green, it's grass. Seems to be at this length scale a uniform field of grass. I would say that this is a homogeneous field of green grass, different from something that is heterogeneous or variable throughout composition. At this length scale, depending on where I point onto the campus itself, I may hit a parking lot, which is concrete, very much the same concrete as in the buildings, but of course assembled in a different structure, and obviously distinguishable at this length scale as being different or variable in composition. Some of it is parking lots, some of it is buildings, some of it is construction sites, so on and so forth. As chemists, we are concerned about zooming in from the observable scale, which we see with our naked eye, all the way down to the atomistic scale, because as we change length scale, this assessment of homogeneous or heterogeneous might change. If we were to zoom on this athletics field, where previously we saw sort of uniform, nice, homogeneous green grass, we'll see that there's actually some variability to it. There's a soccer goal there. There are some lines in the field from where the lawnmower rode through. So there's some variability, some heterogeneity as we zoom in closer. If we were to zoom in all the way down to our individual level, made with a microscope, we would see that this very uniform green grass is actually composed of a lot of different very variable things. There's insects, there's flowers, there's clovers, there's grasses, many different things now that we've zoomed into this particular length scale. As chemists, we have to be mindful of these different length scales that we talk about things. We typically talk about things as the naked eye perspective, as well as at the atomistic or molecule by molecule level. If we were to zoom in on these three materials, which at this point we can obviously see that they're quite different with our naked eye, but if we were to zoom into them on the atomic level, what we might see with a very, very strong microscope is that our diamond is this sort of lattice, this sort of crystalline structure of a lot of the same type of atom, the same type of element, the same little hard spherical balls, same spherical atoms. We notice that this diamond only has one type of particle or one type of atom, and that differs from the dry ice, of which if we zoom back to this atomic level, we would see a different structure, a different arrangement of those same types of atoms, now including both a black one, we'll eventually learn as carbon, and a different one of a different reactivity, a different mass, of different properties corresponding in this case to oxygen. We would, however, see that every sort of cluster of atoms all behaves the same as all this sort of 1-to-2 ratio of one black one to two red ones. If we were to zoom in on the crude oil, we would see a big mess of different things. Not only do our clusters now contain different types of spherical particles, different types of atoms, here including carbon in black, oxygen in red, and hydrogen in white, but now each of those individual clusters, or the individual molecules, are arranged in different patterns, some having 2 carbons versus 4 carbons, and many other permutations in between. One of the big ways that we classify matter is as whether it is a pure element, something that consists of only one type of element, one of the 118 and counting from our periodic table. These pure elements might exist as different things, might exist as single atoms versus large crystals, but all contain just one type of element. That distinguishes it from a compound. These compounds all feature at least 2, many times more, at least two different elements who are held together in these little clusters we call molecules. These molecules are held together by chemical bonds, this type of force that we'll talk more about beginning next week and the week after. But we'll also see something interesting, that whenever we have these compounds, that the arrangement as well as the ratio of each of these elements is a very specific arrangement and a very specific number. We will see one molecule, such as CO2, that always appears as this linear arrangement of one black carbon in the middle, two red oxygens on each side. Always the same arrangement, always the same ratio, no variability in between them. We'll eventually learn that the ratio, as well as this arrangement, this structure, is really what gives a lot of these chemicals different properties. Why we might drink something like H2O, water, with a 2-to-1 arrangement, but would not want to drink something like hydrogen peroxide, which is the same hydrogen oxygen, but a different arrangement, a different ratio of those elements. Finally, the last thing, of course, is our mixtures. These are mixtures of several compounds or several elements combined together. They're held together by a different type of so-called intermolecular force that we'll talk about when we talk about gases and bulk structures. But this is, of course, where we begin to experience a lot more of the chemistry which we encounter in our daily life, in which we have many different molecules mingling around together. Now, other ways that we might classify mixtures is helpful again when we think about this length scale. We will experience ourselves, both in our daily lives and of course in laboratory, different types of mixtures, different combinations of different elements. These different mixtures we classify as either being homogeneous or of course heterogeneous. These homogeneous mixtures include things like solutions, which we count as being dissolved or uniform down to the individual atom level. If we were to zoom in very deeply to a bag of saline, to a cup of salt water, we would see that the sodium and chlorine ions in that water are uniformly distributed down to the individual atom level, that regardless of where I point, every sort of local atom environment looks exactly the same. That is a little different than what we may talk about as a colloid or suspension, in which to our naked eye they still appear fairly homogeneous, fairly uniform. But as we zoom down to the microscopic and atomistic level, we now see variability. You see here two different microscope images of milk, one being breast milk, the other being formula. Breast milk, of course, coming from feeding mothers, and formula coming from a powder that gets dissolved in water. And while both of these substances appear as a uniform, opaque white, a homogeneous mixture to our naked eye, as we zoom down to the microscopic molecular level, we begin to see that our breast milk has little clusters of cells of different fats and proteins grouped together that creates different regions compared to the surrounding liquid around it. That is different than our formula, which is sort of a product of chemistry, that is much more uniform, much more like a solution down to this atomistic level. The final thing, of course, that we see are heterogeneous mixtures. We see this a lot in chemical reactions in which we see very, very obvious separation between different compounds, things like sand versus water versus oil, not forming a solution or a colloid, but giving us very, very obvious, to our naked eye, differences in their composition and their regions. We keep these definitions in mind because we'll be seeing a lot of these things throughout our time in lab, and it's helpful to be able to reference these different definitions as we go through. Now, we'll be moving essentially through this list of different classified substances throughout this course. We'll first start with elements and figure out how do we predict the properties of elements. We'll then work our way through trying to predict how do these elements combine into compounds to make molecules, and then ultimately how these compounds combine together to make different mixtures with different properties. And of course, accordingly, we'll start with discussing elements a little bit today, a lot more next week. Now, the one unifying thing about elements is that they contain only one type of element, one of our 118 from our periodic table, but how those individual spherical particles of atoms might appear vary differently depending on those properties of those elements, which we'll talk about next week. In some instances, we'll see that these pure elements, something like helium gas found in the top right of that periodic table, does indeed exist as a single spherical atom, a single hard little particle bouncing around in something like a helium balloon. However, not every gas that exists as a pure element does behave that way. Something like oxygen, which is of course the element that we breathe, only contains oxygen, again in that top right of our periodic table. So it's still a pure element, but oxygen tends to travel in pairs, forming these diatomic molecules, so two oxygens always moving together as a set. Still a pure element, but a different arrangement of these atoms, now as a molecule of a pure element. Many more, of course, will exist as large crystals, solid things that we might touch. A roll of aluminum foil is still a pure element, only containing aluminum from our periodic table, but of course represents many, many crystals, many atoms bonded together. One thing I encourage you to get into the habit of, if it's not currently a thing that you do, is that because a lot of what we do in chemistry is ultimately quite invisible to our naked eye, it requires us to have relatively good mental models of what's going on. If you're not a person who's great on visualizing or daydreaming, I'm personally very much a person who likes to draw little cartoons. And the more we can represent the invisible atomic world with little cartoons of little spheres and squares and triangles, the better we can get an instinct of how these things might behave. So I encourage you that when we think about pure elements, if we talk about something like helium, which exists as an individual atom, to imagine individual hard spheres of this helium element bouncing around the interior of this balloon. And that being very different than, for example, the chlorine, which you might use to sterilize a pool, which, like oxygen, carries and travels around in pairs, bouncing around now as this dimer, as these two atoms always moving together, which has influence on their properties. And of course, quite different than aluminum, still a pure element, just one element of our 118, but now arranged in this lattice, this repeating grid of aluminum atoms. All pure elements, but very different forms at the atomic level that give different properties, as we'll see in the coming weeks. Now, one little caveat to everything I just told you. So, we reference this idea of pure elements containing only one element of our 118 found on our periodic table, but this word pure is quite a loaded one. We say a pure element, a pure substance of aluminum foil, for example, that contains just one element, but at what level of precision, or how precise do we mean when we say pure 100% one element? What if it contains 1% of some other element? There's a little bit of a different element or different metal mixed into aluminum foil. Do we consider that to still be a pure element of aluminum? An example might be, so there are places in which we do care about these impurities and places in which we can kind of gloss over them or sort of massage them back. Some places it does really matter how pure, at what level of purity we consider something to be a pure element. An example is a diamond. A diamond is a pure elemental compound, a large crystal of just carbon atoms. And if you have a pure 100% pristine diamond, you have a lovely pure crystalline white diamond that only contains carbon atoms. Now, if you're not terribly rich or you don't have a very expensive lab, chances are you have some lesser diamond, still a diamond, that may have some yellowing or discoloration to it. This yellowing or discoloration comes to it because one out of every billion carbon atoms gets replaced by a nitrogen or a boron or some other element. Now, it is a matter of context whether you say that this slightly yellow diamond is or is not still a diamond. Depending on who you talk to, your answers may differ. This, being a diamond, as far as many chemists are concerned, is still mostly carbon, still behaves very much in the same way that this diamond does behave. So we will consider them both pure elements of carbon, depending on the context. If you're particularly in the business of selling and trading diamonds, you may consider that the only true pure element is this pristine one, and all these other slightly yellow diamonds are some sort of mixture, a different material with different properties, depending on what your context might be. Within this course, we are aware of and we recognize that really nothing in this world, even this diamond, technically is not 100% pure. There's always some little thing that's substituted in there. Everything we deal with is going to be mostly pure, some small percentage of other stuff, these impurities. In most cases, we can generally consider that small impurities, like a little bit of nitrogen in our diamond, we as chemists, and particularly for this class, will consider those still be pure elements as far as we're concerned. There's more specialized topics in chemistry in which we do care about these very, very tiny fractional impurities. If you, for example, were a water chemist caring about the quality of drinking water and of sanitation processes, you might care the difference between a tap water that comes out of your sink that has about 200 parts per million of sand and grit and gravel and other things, which is perfectly fine for us to drink, appears clear to our eyes, doesn't harm our body when we drink it, but that may be a very, very different level of purity than a reverse osmosis ultrafiltration water that is used in advanced manufacturing processes to make things like computer chips and other high-end devices. So again, we talk about this idea of purity, of being only one element, within the context of how pure is pure enough. For this particular course, most of the examples we give are going to be relatively permissive, of saying if it is mostly water, we consider it to behave like water, and we'll point out exceptions when they arise. Now, most of our course, most of our time together is going to be building off of this analysis of what are things made of to try to predict the rules of how those things behave. How can we take the composition, what elements make up this compound or this substance, and use that to predict the properties. How does it behave? Is it flammable? Is it poisonous? Does it explode? And most of these rules are going to be learned throughout this course, but we'll dive in with one very fundamental one. Perhaps, and hopefully you've learned this a little bit in physics or come across this before, but chemistry obeys very much the same laws of physics as the rest of the world, the main one being the conservation of matter, the idea that mass and matter is not created or destroyed, but remains constant throughout any sort of change, physical or chemical. Now, you may observe this if you were a home brewer or you worked in a brewery. You would see that if you sealed your bottle of beer, maybe you were making a mead or something like that. It begins with a mixture of water and sugar. And over time, it undergoes a chemical reaction that turns some of that sugar into carbon dioxide as well as alcohol. A chemical transformation that turns one compound into a different compound. Now, even though it's undergone a change, you would find the mass of that bottle hasn't changed. The mass before and after this chemical process remains the same, because ultimately no matter can be created in the bottle, no matter can be destroyed in the bottle, just shuffled around to different forms. You also see the same thing with batteries, going from one type of lead to another type of lead, releasing energy in the process, undergoing a chemical change, but our batteries in our car and our cell phones do not get heavier and lighter as we use them. It'd be crazy if they did. There are some exceptions to this general rule, this idea that we don't change the amount of matter, we just change and shuffle what's attached to what. This one exception is if you get into the weird world of nuclear chemistry. There we observe a conservation of mass and matter, which we won't touch in this particular course. You'll need to wait for your second semester for that. But with the exception of these weird nuclear chemical reactions, we have a pretty good idea that the mass of our system remains constant before and after any chemical change. Now, a caveat to this is that we don't directly measure mass when we run experiments. We measure weight, which is just a reflection of how a scale, a little spring, measures the effect of gravity on some sort of mass. And it's always helpful to remember that we are only measuring a specific thing, and we have to be aware of what it is actually we're measuring so that we don't draw the wrong conclusion. In many cases, I lay out these rules for you, things like the conservation of mass, and I'm a very trustworthy person. I'm very well informed. I don't lie to you without telling you ahead of time. And you can generally trust me, but you shouldn't trust me at first blush. Every scientist has a healthy dose of skepticism. Anything that you're told, anything you might read on the internet, you should take a moment to think, how can I trust this information? Do I trust the source of this information? Is there a way that I myself can verify that this rule is true? The reason why this course is divided up into lecture as well as lab is that lab is there to give you opportunity to do experiments yourself to verify the things I tell you in lecture are indeed true. I'm not just making things up for my own amusement. In many cases, we'll do experiments to verify the rules that we learn here in lecture, as well as sort of figure out the process of how you might discover new rules. In each case, a little bit of skepticism is important. So we're going to run a little mini experiment here, just sort of in our slides, to say, how do we know mass is conserved? I've told you this, and it makes sense, but how do you know? How can you actually verify this? So we're going to run or watch a demonstration of two different chemical reactions. The first one being the burning of wood/paper, the other being the burning or chemical reaction of steel wool, which is just a pure element of iron. Now, according to the rule that I just laid out on the previous slide, throughout these chemical reactions, the mass of these two systems should remain the same. And if I were to place them on a scale before and after this burning reaction, the mass should be the same. Is that true? If it is not true, what is the difference between these two substances? And there's something that my experiment has not accurately measured, not accurately recorded. So we're into experiments. If you don't tell anybody, I told you so. These are things you can do on your own at home. They're not terribly dangerous, but I will not accept liability for it. In the first one, we're going to look at this experiment in which we're going to weigh the mass of a bit of paper before. We're going to burn that paper, undergo a chemical reaction, and then may weigh the remaining mass of whatever is left, the ash, to see, do we conserve mass in that reaction? So we're going to weigh a little beaker with paper in it, record that mass, and then light that paper on fire. It undergoes a chemical reaction. We see the physical appearance of this paper changing, and probably we burned paper before, so it may not be surprising that it looks like we get less paper at the end of this reaction. Looking at our data, the mass of my beaker plus the paper is 416 before and 410 after this chemical reaction. So assuming that my scale is properly calibrated, the result seems to suggest that in this chemical reaction that I lose mass, which seems to violate the very rule that I just tried to convince you of. Let's run another experiment. We'll now do steel wool, which is just sort of this very fine, high surface area iron. And we'll do the same exact reaction. We're going to weigh it before. This is about 409 grams. Steel wool, even though it's iron, does burn. And you see this very, very beautiful sort of propagating orange glow as the iron burns in the presence of air. And then we'll measure the mass of that steel wool after that we've burned it. Oddly enough, we see sort of two problems. One, both my paper and my steel wool have changed mass after this chemical reaction, which doesn't look too good for this rule. But they've also changed in different directions. My paper lost mass, which maybe makes some sense since we've burned things before. But we see that my steel wool, also a burning process initiated by a little flame, has now seemed to gain mass, has gained about 2 grams, as opposed to losing that 2 grams. Our experiment, intended to verify this conservation of mass, gives us two problems again. We see a decrease in the paper and an increase in the mass of our steel wool. And the question now becomes, from this experiment, why do they behave differently? Why does one decrease and one increase, both burning? And neither of them seem to obey the law that I've tried to convince you of. Now, you're welcome to sort of leave and quit this course because I've lied to you seemingly once. But I ask for you to sort of hold on. Obviously, one day of chemistry isn't enough to predict how the whole world behaves. Some rules and some laws that we will learn will seem counterintuitive at first. We know that paper gets smaller and lighter as we burn it, so it doesn't make sense that masses should remain the same. But we have to be careful and mindful of what we're actually measuring in this experiment. We're not measuring the mass of that system, just one part of that system, the paper and the ash residue left over. As we learn more chemistry and we work through this analysis of chemical reactions, we endeavor to try to, one, understand the full meaning of these rules and of these laws and how you actually would verify and measure them. But it does take a little bit of time. It does take a couple of weeks worth of material. And so this puzzling result, which we seem to violate the very first rule that I've told you, we'll come back to in a couple of weeks as we start to talk about chemical reactions, not just what things are made out of. So there's many ways that you can figure out and describe the rules of polar bears and fishes, and they're all equally valid, but they approach them from different perspectives. And chemistry is very similar in that respect. There are conceptual ways that you can approach chemistry that help interpret the physical world around us. Our sort of rule, or the rule that I follow for polar bears and fishes, is that any odd numbered dice face that points up, because it's odd, you'll notice that all the odd dice have a hole, a dot, very much in the center of the dice. And around that central dot, which represents the hole in the ice, sits an even number of dots, polar bears. And I can count the number of polar bears based off of how many are around that central dot. And then intuitively, the thing on the number of dots on the opposite face, on the bottom one on the table, is what's under the ice. And that represents the number of fishes, but only if there's a hole present. So you can look at the dice and you can interpret visually what they mean, what they represent. There's also math, and there's many elements of chemistry that math is a much more convenient explanation. The other way you could figure it out is that you could take, and according to a equation that you can write, and we'll work with equations, so I suggest you don't shy away from them, is that the number of polar bears is adding up all of the odd numbered dice, or odd valued dice, and from that, I made a mistake. It should be subtracting 1. So the dice face shows 3. I subtract 1 because it represents the whole. So there's only 2 polar bears associated with that. I can approach that conceptually, but I can also approach that much more mathematically, depending on your bent. Again, that should be -1. I'll make a correction in the updated slides. Fish also works very much same thing, where for every odd numbered dice, you'll notice that the opposing faces of dice, a rule of how dice are made, the opposing faces of dice always add up to 7, 1 and 6, 2 and 5, 3 and 4, which is why I did not need to lift up your dice to figure out how many fish there were. And so you have another equation, a mathematical way to interpret this physical phenomenon. Importantly also, there are things that don't matter, or at least not matter to this particular rule. A lot of things we can describe about chemicals, the shape of a bottle of chemicals, the color of the powder, how large the particles are. Sometimes it matters, sometimes it doesn't. For each of these rules, we have to be able to discern between the aspects that dictate their properties and the rules versus things that may be trivial. It doesn't matter what color the dice is. It doesn't matter what size the dice are or where they're located with respect to each other. And so this is very much the mode that we will pursue here in chemistry as well. In the last little portion, we're going to begin our discussion of measurements in chemistry. Very much, unfortunately, everyone's least favorite aspect of it, so we'll touch on it now and we'll reinforce on Wednesday when we do measurements in lab. But also, this is of course relevant to our first problem set. It's very hard to do chemistry if you don't know how to measure things. Same way as it's hard to play polar bears and fishes if you don't know how to count, very simply. So we begin sort of talking about how chemists talk about measurements. And really, all of our measurements are math plus probably previous experience we've had in measuring things and counting things. The thing that we impress upon you is the idea that we adhere to a standard way that we talk about measuring and counting things so that our results can be interpreted by other scientists and chemists appropriate to what we actually measured and vice versa. One thing that I will repeat often is that scientists are very, very particular about the letters and symbols that they use to describe stuff. There's only 26 letters in the alphabet and a fewer number of Greek letters. And so with that limited set, we have to describe the near infinite things that exist in this world. For that, it's very important that both your typing and reading, but also your handwriting, is able to distinguish between different types of letters. Opportunities to practice and get feedback, but be very mindful that if you are the type of person whose handwriting does not distinguish between capital and lowercase letters, you're going to have a very hard time in chemistry, as these things mean something different. It's also easy to mistake things like a capital I versus a lowercase l, which mean, again, very, very different things. So be mindful of your handwriting. The Greek versus Roman or Latin letters mean different things, although they might look similar. Again, we'll practice this throughout the rest of this course, as well as the upper and lower case for things like unit abbreviations. Again, mean different things in chemistry. And to be very precise and to represent what it is we measure, we have to follow some of these more precise conventions. Eventually, we'll talk about numerical things, and so we'll also work with things like subscripts and superscripts that follow things within a chemical formula, for example. Again, which, to be the most precise and correct, requires a little bit of attention to detail. In most instances, though, our time will be spent trying to describe things, first as we would normally as people, but then moving towards more precise descriptions as chemists would. So as a normal person, you might see this pink pigmented powder. And we probably are already equipped to make relatively qualitative descriptions, things that use words to describe the quality of something. We might say that this powder is a pink color. We might say that's very finely textured, that has very small particles. And these are helpful, useful, just the way we describe sort of the shapes of the dice and their dice faces. We may also be equipped already to make comparative measurements and description to say that because this powder sinks in water, we know that it's denser than water. As chemists and as scientists more broadly, we move towards trying to make quantitative description and measurements of these same types of properties to be more precise about their value. Every sort of measurement, quantitative measurement we make, exists on some sort of scale, some sort of reference that we can rank it. Every measurement that we make is going to consist of a value, which is going to be a number, as well as a unit describing what scale we're using it. Saying something has a length of 1 means nothing unless we say it's 1 foot versus 1 meter, again, representing different things from different scales. We can take the same type of qualitative descriptions and in many cases make quantitative descriptions. We may describe the color by their RGB value, in this case representing on this light emission scale that goes between 0 to 255. We might reference not just that it's finely textured or a very small powder, but represent the size of that particle, 0.01 millimeters, a very, very small average particle size. And eventually, we work our way towards being very precise in our chemical description. Not that this is just some pink powder, but in particular that this is a mica silicate mineral that consists of potassium, represented by K, lithium, aluminum, silicon, oxygen, fluorine, and hydrogen. All these ways we'll work towards and build towards throughout this course, but by the end of this course, we'll be adept at making both qualitative descriptions, more importantly, and maybe new, more quantitative descriptions. Most of what we measure are going to adhere to the metric system, which if you were educated outside the US is probably not a big deal. But here in the US, we use imperial units quite commonly. And so it takes a moment to adjust to this system of prefixes. For every sort of unit of measurement, something like a small lowercase g to represent a gram, we have different ways to modify that to represent very large or small versions of the same unit. 1 gram might be modified by a capital G to represent a gigagram. which is 1 billion grams, so it helps to simplify and represent large masses. On the same level, we could also modify with something like the metric prefix of a lowercase n, standing for nano, a nanogram being 1 billionth, or 10 to the minus 9 grams. This scale is something that you are welcome to look up. This is a good example of things in which you should not rely on a faulty memory to remember what these prefixes mean. And I can guarantee that by the end of this course, you'll probably have memorized most, if not all, of this table quite naturally. But this is a good thing to include in a cheat sheet, or at least know where to look up these values very quickly. In many cases, we have a very small handful of units that we actually measure. Again, it's helpful to have only one way that we measure mass. In this case, we measure mass as a function of grams, length as a function of meters, and be able to relate what does a kilometer or kilometer versus a meter versus a micrometer or micron represent in terms of our relative length scale. Kilometers or kilometers, of course, are long distances, about sort of how long people travel to get places. Meters are sort of a human length scale. Most of us are sort of in the neighborhood of 1 to 2 meters. And down to the micrometer scale represents things on the individual cell level. And it's helpful to have a reference point for what these prefixes mean in terms of those length and mass scales. Mass we measure with grams, time we measure in seconds commonly. And in science and engineering, there are a lot of different units we might use. Problem set 1 has you go through a little bit of a scavenger hunt to figure out what are these different units, how do we abbreviate them, what does a ATM measure as a unit of pressure, so on and so forth. So this is an exercise that you'll go through in the first problem set, but of course this is something, again, that the reason why I don't ask you to memorize everything in the world is because there's a lot of units out there, and it's more important that you are able to look up and get the correct unit than to memorize the incorrect wrong unit. Some of the properties we talk about, mass, volume, for example, we refer to as extensive properties. These are ones that vary and are based on the amount of matter present. Obviously, if I have more diamonds, I have a higher mass of diamonds. If I have more diamonds, I have a higher or larger volume of diamonds. These are extensive properties that depend on the amount of matter. A lot of what we deal with in chemistry is an intensive property. In many cases, an intensive property is a ratio between two extensive properties. The density, for example, regardless of whether I have 1 diamond or 1 billion diamonds, every diamond is going to have the same density, the same ratio of grams per milliliter, the mass for a particular volume of diamond. All those diamonds, as well as if I were to place them on the bench top here, will be at the same temperature, regardless of whether I have 1 gram of diamonds or a kilogram of diamonds. This intensive property doesn't change based on how much of that material I have. If we're not terribly familiar with metric units, we will be by the end of this course. I can guarantee that. But I do have some tips and tricks. Problem set 1 is one that does take a moment. And of course, we will be spending some time on Wednesday after we do our lab to sort of go through parts of it together to make sure that we all are on a good footing to begin with. But it is quite foundational. If you don't understand things in problem set 1, the rest of this course will not make any sense. So do take some time to treat it with some care and attention. Most of it's going to be a thing about being very detail-oriented, and chemistry is all about the details. So do pay attention to the letters we use to represent different units or variables. Do pay attention to the case of different letters, since they might represent different things. A lowercase k represents the prefix for kilo, like kilogram, whereas a capital K represents this unit of temperature called Kelvin. Your handwriting, if you handwrite your problem sets, should be able to distinguish between a lowercase k and a capital K. Some of that comes by, and you're welcome to have your own style to it. But you will see that when I handwrite things, that I represent letters in a very, very different way, just to make that apparent. As for K, for example, chemists will often write a lowercase k as a script K, just to make it very, very clear and obvious the difference between that and a capital K. You also see that personally, when I write an I for the element of iodine, I write that different than a lowercase l to represent. I know I don't confuse a capital I for iodine versus a lowercase l for milliliter or part of chlorine. So be very careful, be very, very detail oriented, and it'll pay dividends beyond that. One little note that only applies maybe to some of you, depending on, again, where you learned math, you may come from a country or have been educated in a country that uses a different decimalization. And it really is no rhyme or reason whether or not people use a decimal point or a comma to represent values smaller than 1. The French Canadians, for example, use a comma, and they're only a couple hundred miles away. But just to keep everybody consistent, and typically what's done in science, when we represent large numbers and we separate every thousands, we use either a space, just to show a visual gap between the zeros, or a comma. And to represent a decimal, so something smaller than 1, we will use a decimal point, as opposed to a comma, which is used in a handful or a selection of countries. Once you leave this course, you're welcome to do whatever you like, but at least for us, for me to make sure, we're going to follow this convention. Now, in many cases, we start to work with numbers that have a lot of zeros present in them. And even if we keep commas and decimal points and little spaces, it becomes very, very hard to keep track of very, very big numbers and very, very small numbers. And in this course, we talk about individual atoms. We often talk about large numbers of atoms. For example, if we were to talk about how many atoms of helium are there in a normal sort of 1 liter size balloon, obviously 1 liter is a very easy number to work with, only 2 digits. But there are 4 gazillion and a half atoms of helium in that 1 liter balloon. And it's important that we talk about that number of atoms in a convenient way. If I just write zeros, I'm prone to mistakes, and I don't trust myself to sort of drop a factor of 1,000 here or there. The way as scientists in which we talk about large numbers is that we essentially divide out or remove a certain number of 10 to the power of something. This essentially pulls out all these extra zeros, encapsulating them in this exponential function. So for this very, very large number, we could use scientific notation to represent that as 4.5 times 10 to the power of 21. This is 4.5 times 1 with 21 zeros after it, giving us a much more compact way, much less prone to mistakes, to represent this very, very large number. Part of the reason why we do this, of course, is that we don't just want to represent large numbers for the sake of it, but we have to do calculations quite often to say, if I have that many atoms of helium, how much energy is released when I compress or expand them. I may also say, of that balloon, let's say we fill it with air instead, how many of those air molecules are oxygen, which represents 21% of those atoms or molecules or particles. By using the scientific notation, I can much more easily do math that I could even plug into my calculator. I probably can't plug 21 zeros into my calculator, but I can plug 0.21 or 21% times 4.5. And I can leave this factor of 10 out to the side since it doesn't really modify the result, just the scale of the number of molecules. I'll get some math. In this case, I have 0.21 times 4.5 is 0.95 times 10 to the power 21 molecules. Proper scientific notation, just again to keep standards, has 1 digit to the left of the decimal place. There's always numbers between 1 to 9. And so I need to sort of readjust this number, essentially pushing back a factor of, factor of 10, giving me an answer of 9.5 times 10 to the 20 molecules. There's ample practice in the first problem set, and we'll do some examples together on Wednesday if you hang around for that. Likely, The thing that we need to remind ourselves, if we haven't done this type of math in a while, is that scientific notation requires us to be really good with exponent-based math. Or if I multiply 10 to the power of a times 10 to the power of b, I can add those exponents together. If I divide, I subtract the exponents. And if I do 1 over something that is simply the inverse or the opposite sign, the negative of that same exponent. If I raise that thing to another exponent, that's multiplying the two exponents together, so on and so forth. Again, Problem Set 1 has some opportunities to practice these calculations, and if the math is something we haven't done in quite a while, let me know. I have resources I can point you towards there, but make sure you know how to do the math, since we'll be doing this type of thing time and time again throughout this course. Now, most of the math we do here in chemistry is not going to be terribly complex. It's going to be some sort of algebra, but we have to be very careful about how we do so. In many cases, the thing that we measure is not going to be directly the thing that we care about. For example, in our dice or our polar bears versus fishes game, we counted the number of dots. The number of dots is not directly equal to the number of polar bears and fishes. We have to convert that number of dots into something else. And quite often we utilize what we call a conversion factor to go between a thing that we measure versus a value we might actually care about. In those instances, this number, the value, the thing we measure doesn't change, but how we interpret what scale we might use might be a different thing. A common way we might do is if we convert between imperial units, like pounds or feet, and converting to metric units, we need a conversion factor that relates one unit to the other. In many cases, let's say we want to figure out if someone weighed 120 pounds, how many kilograms does that mean? Importantly, we don't want to change the mass of that person. We just want to know what their weight is in a different unit. For that, we need to find a conversion factor, which is really a ratio between my two units. Conversion factors are things that, again, you will begin to memorize as we go through them. Some of them you can sort of guess or deduce. But in many cases, these are important things that are worth looking up, worth double checking a reliable resource. And again, we'll go through some examples on Wednesday. A ratio should always relate the number of one unit to the number of a different unit. So for example, I know that 1 kilogram is equal to 2.2 pounds with some maybe extra decimal points. A conversion factor is essentially a ratio which equals 1. In which case, this conversion factor says that a 1-to-1 ratio is 1 kilogram divided by 2.2 pounds. Now, the way I use this conversion factor is a little like this. You're welcome to approach it differently, but this is my process and the way that I'm best equipped to advise on. We set up ourselves an equation, and we begin with the value that we know. In this case, we know this person weighs 120 pounds, and we want to map out where we want to get to. We want to convert that to some units of kilograms. We need to multiply or divide this initial number, 120 pounds, by as many conversion factors to go between one unit to the other. In many cases, we first need to assemble all those conversion factors and sort of use them like a toolbox, like a game of dominoes, you might say. In which case, in this one, I have one conversion factor that relates the number of pounds to the number of kilograms. I have to make a choice. In each of these things, I can either multiply or divide by my conversion factor, and it's not arbitrary. There's ways to figure it out. And we largely do so by doing either called dimensional analysis, or more commonly, or more or less fancily, making sure that the units cancel out. When I set up this equation, just as I can multiply and divide these numbers, I can also multiply and divide these units. This equation essentially says 120 times 1 divided by 2.2, as well as pounds times kilogram divided by pounds. In the same way that I can do math with numbers, I can do math with units. In this case, because I have both pounds in my numerator and pounds in my denominator, these pounds will cancel each other out. And I'm only left with the unit of a kilogram, which is why my final answer will be 55 kilograms. I do the math, I plug the numbers in, I make sure the units cancel out, and I'm only left with my desired unit at the end of the day. I know that I have to divide by 2.2, because that's the only way to make these units cancel out. If I multiply by 2.2, I'd end up with something weird like pounds squared per kilogram, which is not a real sensible thing. This is a big case in which if you're not the type of person who likes to show your work in problem sets or on exams, I strongly encourage you to write things out. It helps you prevent or helps you catch your own mistakes. It also helps me see what you're doing so I know how to help you. So if you're not the type of person who likes to show their work, this is a good time to get into that habit. In many cases, our conversion factors will be a lot more complicated, moving not between units of the same property, but between very different unrelated units. So let's say I wanted to calculate how many hours I would spend on the t coming to this class. How would I measure that, and how would I calculate this value? Well, to calculate or estimate, I have to start with something that I know, and I don't really have the time or energy or effort to spend one semester timing myself every time I get on and off the t. But I can estimate it based on something I can measure much more quickly. And I can count the number of semesters and how many hours are in one semester worth of class time. But how many hours I would spend on the t. I can begin to assemble conversion factors, things that relate a semester's worth of class to something else, eventually hours spent on the t. Some of these things are things I can guess or I can deduce. Others I might have to look up or measure. But for a normal fall or spring semester, I can count that there are 16 weeks per semester. This is a conversion factor, 16 weeks to one semester. I know my class, maybe this is a lecture class. I come to class one day out of the week. To get to Bunker Hill and go back, I have to take 2 trips per day. And I can measure something that says that on the average trip, I'll measure it once. It took me between about 30 to 15 minutes. And I'll take an average of maybe 40 minutes to get to class on the t. I can also pull together standard definitions that there are 60 minutes to 1 hour. And now I have to begin to assemble this conversion factor equation. I'll give you the result. Ultimately, I have to decide for all my conversion factors to go from one semester to the number of hours spent on the t. I have to decide which to multiply and divide by. In each case, the thing that I'm trying to aim for is to make sure that my units cancel out at the end. In this case, by multiplying by 16 weeks per semester, my semesters cancel out. My weeks will cancel out, my unit of day will cancel out, my unit of trips will cancel out, my units of minutes will cancel out, leaving with only one unit left over, hours, which tells me I multiply and divide things as I'm supposed to. I'll calculate this out to about 21.3 repeating hours, and I'll round that to about 20 hours or so. Again, seeing that my units are only left with the one that I am looking for, the hours spent on the t. Write your equations so you can help double check yourself as you go through this work. Now, one of my conversion factors was kind of a guess. It's something that I measured, and obviously there's variability in the t. Some trips are a little faster, most are a little slower. And my estimate really represented that there was a range of values and an uncertainty on what every trip on the t would be. It's between 30 to 15 minutes, so it's a reasonable thing to take an average of 40 minutes. But there's an uncertainty to that, and I can't absolutely guarantee that every trip will take 40 minutes. This is something we deal with quite commonly in chemistry. There are some things that we have exact knowledge of. Things like, I know there are exactly 60 minutes per hour. There's no uncertainty about that. That's the definition of an hour. And I can count the number of weeks in the semester. That's not going to be variable for the semester. But of course, much of what we do is going to have some measure of range or uncertainty in that property or that factor. All of this influences how precisely I can say my final answer. If I have a relatively large range of my estimated time per trip, 30 to 50 minutes, it might seem a little disingenuous to say that I know my total travel time this semester will be 21.3333 hours, it seems too precise for how imprecise my estimate of 40 minutes is. In chemistry, potentially more than most sciences, we really care about not overestimating or underestimating these calculated results to represent how confident we are in any given one measurement. For that, we have to keep track of and calculate according to this concept of significant figures, or sig figs, as can be sometimes called. And it is everyone's least favorite part of it, but quite important, as we'll show in a moment. Now, these sig figs represent that anytime we measure something, there's not a perfect level of precision. There's always some uncertainty. Most tools, and we'll talk about this on Wednesday, have some measurement of how precise they are versus how accurate they are. Two different concepts. We sort of use the analogy of this target, in which if we were to shoot at this 10 to 20 times, how accurate our shot is versus how precise our shot is means different thing. If we were to say we had a very precise shot, that would mean that every time we shot this target, every time we took a measurement, all those values would be clustered very, very close together, a very small range of values. That doesn't mean that they're clustered around the true measurement, the true length of our trip, the true mass of our person, but they're all clustered very closely and they all agree with each other. That is, of course, different than something that is very accurate, that might be relatively spread out. Every time we measure it might be high, low, but on average, it gives the correct number, represented by something that might be accurate, but not precise. In many cases, we'll explore here in lab the difference between having accurate versus precise results. And in this particular case, sig figs are a measurement of precision. How closely are our measurements to each other every time we do a measurement? It doesn't mean that necessarily it actually took 40 minutes for us to deride the t, but every time we measured it, it was relatively closely clustered together between 30 to 50 minutes. When we do these measurements in real life, and we'll again practice this extensively on Wednesday, our precision is really limited by the tool that we use. If we want to measure the length of this fish, which we won't be measuring lengths of fish, but it's a good illustrative example, how precisely we can represent the length of this fish depends on the ruler that we might use. We'll see that this ruler up top doesn't have many lines. It's a relatively imprecise ruler. When we look at this ruler, we can say that the length of the fish falls somewhere between 50 to 60 centimeters. And a reasonable scientist, one that we've all agreed, or a convention that we've all agreed upon, is that we can estimate one more digit beyond the number that we count. I can count that this fish is at least 50 centimeters, and I'll estimate the number of 1 centimeters that this fish is. You might say 54, I might say 53, but we all agree it's 50-something centimeters. That precision is very different if I were to use the bottom rule, which has more tick marks, which has more precision. We can both agree that this fish is at least 53 centimeters, but that extra fraction we might disagree on as scientists, but we're always allowed to estimate. I might say 53.5, you may say 53.6, but we all sort of agree on the counted digits. When we track sig figs, we really only care about the digits, the parts of the measurement that are numbers that we count, and one more digit that we estimate. All of them are significant. All of them represent something that was measured. And so our significant figures counts the number of digits or number of tick marks that we can count and all agree upon exactly, plus one more digit, in many cases one more decimal point that we are all free to have a different interpretation of, but truncates where we're starting to guess on this measurement. Even if we were to have a fish that landed exactly on a tick mark, we need to still record zeros and record that it was 53.0, for example, just to hold the place and represent what number we're all estimating and which number we all counted and agreed upon. We'll see this with a lot of the tools that we use. If you use a thermometer, really any analog tool that has tick marks in a scale, we'll need to count and represent how precise this thermometer was. The fact that there's a line every 1 degree Celsius means something very different than if there was only a line every 10 degrees Celsius. Different tool, different precision, different certainty of what this temperature might be. The easiest thing, and one reason why many scientists will use digital tools like a mass balance or scale, is that the digital tool, the display, will count and estimate the one more digit for us. In many cases, we simply write down and record the value that is displayed. If we were to weigh something in the lab that weighed 2.334 grams, the scale has already done the work of a scientist to estimate that this 4 is an estimate. We're confident about the 2, the 3, and the 3, but the scale has estimated this 4 for us. The interpretation, of course, is that the scale, in its weird estimation, is only confident it's maybe between 2.33 and 2.335, estimating that final digit, but is confident of the 2, the 3, and the 3. Why do we care about this? Ultimately, precision is a measurement of how confident we are in a particular measurement, and it's particularly important when we deal with very, very small numbers and very, very large numbers. An example, if we, for example, need to give a baby, which is most of my days now, some sort of medicine, it really matters how precisely we know the weight of that baby. If you were to casually say that your baby weighs 10 pounds and give them a very potent toxic drug that has to be dosed very appropriately, not too much because that might hurt the baby, not too little because you might not see an effect, it really matters whether or not you're confident that the baby weighs 10 pounds or 10.0 pounds or 10.00 pounds, because there is a different estimate of range. If I said just 10 pounds, it might imply that I'm really only confident the baby weighs between 9 to 11 pounds, versus 10.0 pounds gives me a tighter range. At the far extreme, if I only have one significant figure, one estimated digit, that implies I'm only confident the baby weighs somewhere between 0 to 20 pounds, which is not a very useful measurement, not very precise. In many cases, of course, we agree that this is the rules of sig figs. We count all of them, we include all the counted ones, and we estimate only one. And we do so largely so we can all agree on how precise each of our measurements were.